Okay, so now we're going to move on to section 6C, and we're going to talk about the normal distribution. The normal distribution is a symmetric bell-shaped distribution with a single peak. Its peak corresponds to the mean, median, and mode of the distribution. Its variation is characterized by the standard deviation of the distribution. Now, in the previous lesson, we talked about standard deviation, and basically standard deviation shows you how far the values differ from that mean value that's right in the middle, the mean, median, mode. It'll show you how far to the right or the left they are, and so we're going to use that now with the normal distribution. Sometimes the normal distribution is referred to as the bell curve, so you may have heard that before. So let's use some data sets and talk about how we do this. In this figure, you are shown two distributions. The first one is a famous data set of the chest sizes of 5,738 Scottish militiamen collected in about 1846. And the second one, part B there, is the distribution of the population densities in the 50 states. Is either distribution a normal distribution? That's what we're trying to decide right now. So you can actually take a look at it. If it is a normal distribution, it says that it's going to be bell-shaped with a single peak, and the variation is characterized by the standard deviation of the distribution. So what we see here is it does have that, the first one has this bell shape, if you were to kind of go across the tops of those. And you can see that bell shape occurring there. And then the second one kind of tapers off with the tail towards the right end. And so if it's a normal distribution, you're going to see that the more symmetrical view that you see here. So we're going to come over here just so you have a chance to write down what we've talked about so far. The distribution of the chest sizes in figure 615 is nearly symmetric with a mean of 39 and 40 inches. Values far from the mean are less common. There are very few that are out to the left or to the right. And so if those values are less common to the left and to the right, then this is what we call a normal distribution. Okay, like I said, it's going to have that bell shape. The distribution in 615 part B, though, shows that most states have low population densities, but a few have a much higher density, and this fact makes the distribution what we call right skewed, which might look a little bit more like this, where there's a tail off to the right. And so you might want to make yourself just a little note that the tail of the data is on the right when it's right skewed. So that one's not a normal distribution. So just coming back here to our picture real quick, so we can say that this one right here, the first one, the chest sizes would be normal, and that this one that shows our population density with the tail going off to the right is what we call right skewed. Okay, so coming back over here, let's look at the conditions for a normal distribution. A data set satisfying the following criteria is likely to have a nearly normal distribution. First off, most data values are going to be clustered near the mean, giving the distribution a well-defined single peak, so they're going to be clustered towards the middle, which is what gives you that peak that you see. The data values are spread evenly around the mean, making the distribution symmetric. So there might be some before and some after, but they're spread fairly evenly out. So it comes down and has that symmetrical view where it looks like you could fold it and it would match. Larger deviations from the mean are increasingly rare, producing the tapering tails of the distribution. So you'll see just a few to the left, just a few to the right, just pretty far away. It says here larger deviations, so those are the ones a little further away, which is what makes that tail that comes out to each side. And then individual data values result from a combination of many different factors. Okay, so here's an example of deciding again if it's a normal distribution. So it says, which of the following variables would you expect to have a normal or nearly normal distribution? The first example is the scores on a very easy test, and then the second one is the foot length of a random sample of adult women. So as far as the scores on a very easy test, the test has a maximum score of 100%. It limits the size of the data values, and if it's very easy, then we assume the mean's going to be high because most of the scores will be high, and they'll be clustered up towards the top with the higher scores, and many scores will be near this maximum. The few lower scores can be spread out well below the mean, So there might be a few lower scores that are over here to the left. Therefore, we would expect this to be left skewed. So there might be a few a little bit lower, but there's a limit to how far these scores can reach as far as height. They have to end at some point. They cannot continue on and on and on because it does limit it to 100. Okay, so our data might look a little bit more like this, where they're mostly clustered up here, and that's going to be where our average score is, and there'll just be a few out here to this one side. So it's what we call left skewed, and it's not a normal distribution. But that second example about foot length is a human trait. It's determined by many genetic and environmental factors. We therefore expect the lengths of women's feet to cluster near a mean and become less common farther from the mean in both directions, giving the distribution a bell shape, like the normal distribution. Okay. Because again, we kind of talked about this with women heights, that there's going to be towards the center where most of the women cluster in their height, and then it's going to taper, a few are shorter, a few are taller. Well, the same thing's going to happen with foot length. There's an average foot length for the random adult women, and then there'll be a few that are smaller and a few that are larger, so it is going to make that bell shape. Okay, now there's a rule for distribution, the normal distribution, and the rule for the normal distribution is the 68, 95, 99.7 rule. And basically it shows you that 68% of your data is going to fall in this region right here, this darkest gray in the middle. 68% of your data is going to fall right here within this region. 95% is going to fall within this region. And then 99.7% will fall between this region. So that's just about all of your data. By the time you get to the bottom there, you can see that just about all your data, all but 0.3%, is going to fall within that region. Now, the way that this is determined, this 68% falling within this region, if you look down here, it shows you that it's got this plus and then this symbol right here. This represents one standard deviation. And then you can see right here, this represents 2 standard deviations. And this represents 3 standard deviations. Now this would be 1, 2, or 3 standard deviations above your mean because they're on that positive side to the right. And then you'll notice right here that the same thing has happened on the other side, but these are below it. So this would be 1 standard deviation below, 2 standard deviations below, and 3 standard deviations below the mean. Okay? So we're going to be doing an example of that in just a moment. So about 68%, more precisely 68.3%, or just over 2/3 of the data points will fall within 1 standard deviation of the mean. About 95% of the data points will fall within 2 standard deviations of the mean. 99.7% will fall within 3. And then this rule applies to data values that are exactly 1, 2, or 3 standard deviations from the mean. Okay, so coming up here, you can see this, that like this is marked off from here to here. This is the distance of 1 standard deviation. And you can have that also happening here to the left. So it's either 1 standard deviation to the left or it's 1 standard deviation to the right. And it says 68% of our data values will fall within this space right here, where they are 1 away on either side. And then you can see this 95% range right here. You're seeing that this is 1, 2 standard deviations to the left, or 1, 2 standard deviations to the right. And here's our 1, 2, and 3, and then 1, 2, and 3. Okay, so just an example here. The SAT test, let's talk about that for just a moment. The mean SAT score, would, if it's 500, which is generally approximately 500, with a standard deviation of 100 points, then we know that 68% of the people who take this test should score between 400 and 600. We know that because the standard deviation, or 1 standard deviation, is 100 points. So if you were to take 500 and go 100 above it, you get 600. If you were to take 500 and go 100 below it, you get 400. So we know that this range, if this were our graph to match this information, this will be going from 400 to 600 points right there. And so these people in this shaded region right here are scoring between 400 and 600 points right here in the middle. Okay, that's one standard deviation to the left or to the right. Now, 95% are going to score from 3 to 700. Okay, so this would be right over here. This represents 300. This represents 700. Okay, and so what that means, this is 2 standard deviations away because 300 is 200 below 500, and 700 is 200 above 500. So remember, 500 would be our mean right there in the middle. And then 3 standard deviations away would be going back 300 before 500, which takes you to 200, and then 300 above it, which takes you to 800. So we know that 99.7% are going to score between a 200 and an 800 on that SAT score. Okay, so now let's do an example using this as well. Vending machines can be adjusted to reject coins above and below certain weights. The weight of legal U.S. quarters are normally distributed with a mean of 5.67 grams and a standard deviation of 0.0700 grams. If a vending machine is adjusted to reject quarters that weigh more than 5.81 grams and less than 5.53 grams, what percentage of legal quarters will be rejected by the machine? So we already know one important thing right up here, and that's that one standard deviation is 0.0700. We know that for sure. Okay, so it says that it's going to be rejected if it's more than 5.81 and less than 5.53. Now, since we already know that the mean is 5.67, we're just going to see how far that 5.81 and that 5.53 are from the mean. So to find the distance from 5.81 to 5.67, we just subtract and we get that it is 0.14 grams, and 5.81 is actually 0.14 grams above 5.67. We do the same thing over here with our subtraction, but since 5.53 is below, we're going to begin with the 5.67 and subtract the 5.53. It's 0.14 grams below the average of 5.67. Now, we already know that 0.0700 is one standard deviation, and we see that these are 0.14 above and 0.14 below. Well, 0.14 is equal to 0.07 times 2. Okay, which means that we have taken one standard deviation and doubled it. So that means that 0.14 is actually equal to 2 standard deviations. So this machine is actually accepting anything that is 2 standard deviations above the mean or 2 standard deviations below the mean. Therefore, by accepting the quarters within this weight range, the machine accepts quarters that are within 2 standard deviations and rejects those that are more than 2 standard deviations from the mean. And we know from the 68, 95, 99.7 rule that this 68 is going to be within 1 standard deviation, 95 are going to be within 2 standard deviations, and 99.7 are going to be within 3 standard deviations. So we just discovered that our amounts are within 2 standard deviations, and that corresponds with the 95, which tells us that 95% of our quarters will be accepted. And that means about 5% of them will not. Since 95 are being accepted, we just subtract that from 100%. So we have 5% that are not going to be accepted, so they will be rejected. Okay, and so we do have a little bit more to do in this section, but that's going to end this first video, so make sure you tune in to part 2.